Mr. Ford here. In this video, I'm going to be going over lessons 1, 2, 3, 4, 5, and 7 from Unit 7 on circles in our illustrative math workbooks. So these are basically all the things we covered on the week before Thanksgiving. We covered lesson 1 and 2 on Monday. We covered lesson 3 and 4 on Tuesday. 5 and 7 on Wednesday, and then on Thursday we got into 8 and 10, but I'm going to save those for another video. So I'm just going to do those things we went over Monday through Wednesday as sort of a recap for those of you that may have been absent or may not have caught everything, because I know the week before a holiday, a lot of times students are absent or they're making up work for other teachers or, just generally distracted uh, because of the holiday that's coming up, right? Everybody's excited about being off for a week and having Thanksgiving and the things that they potentially will do during that time. So sometimes we lose track and we get a little distracted. So this video is going over those things, and this is all dealing with circles. So it's really easy. It's really uh, easy concepts to grasp, easy things to identify, but very important because when you take the LEAP test, circles are a big part of geometry, high school geometry, and they lean heavily on the things that you're learning. And in particular, the things that are in this video itself, because there's a lot of information that you need to know, and it's not things that are going to be, you know, sought directly. It's basically that background information you need. So lesson one, I'm just going to go over the lesson summaries from each lesson, and then I'll give a couple of examples. So lesson one introduces diameters and chords, central angles, and arcs. So diameters and radii are two types of line segments that appear in circles. Here are some additional geometric objects associated with circles. A chord, a chord is a line segment whose endpoints are on the circle, right? So here's a line segment. It's important that it's just a segment, not a full line, with endpoints on the circle, right? So the example below, this is a chord because it has endpoints on the circle. The endpoints of G and H are actually on the circle. Now, chords have there's several different types of chords. But if a chord goes through the center right here, this point, for instance, if I have a chord that goes from one side through the center to the other side, then that chord is a special type of chord that's called a diameter, right? A diameter. So we've talked before about diameter being the length across a circle from side to side and it going through the center, right? We've also talked about a diameter being twice the size of the radius, right? But a diameter, by definition, is actually a chord that passes through the center of the circle. Okay, so those are chords, and we're going to see several examples of them. A central angle in a circle is an angle whose vertex is at the center of the circle, right? So vertex at the center. So let me underline that too. Vertex at the center, and that's a central angle. So down below, this is a central angle, right? And a central angle is going to be relative to the arc that it creates, right? The arc that it creates. So that's the next definition. An arc an arc is the portion of the circle between 2 points on the circle, right? So the portion of the circle between 2 points on the circle. So this is an arc here. Let me just erase those edges where I went over. All right. So there's a special relationship between the arcs of a circle and either the central angle or the inscribed angle, which is something we're going to learn about next, that comes up in lesson 2. And that is one of those things that you need to know. You're expected to know this, you're expected to identify, recognize it, and use it in the application or computation of whatever problem they're giving you, right? So the measure of an arc is defined as the measure of the central angle formed by the radii drawn to the endpoints of the arc. And that's a long, complicated definition, basically meaning this arc length is relative to this angle measure, right? So if this angle measure is, let's say, 25 degrees, then this arc length would be 25 degrees, okay? But that is only the case when it's a central angle, when it's an angle that's vertexes at the center. There's going to be exceptions when the angle is not at the center, and that's one of the things we're going to talk about, right? Actually, I'm just realizing that the example they give here in the lesson summary is a 45 degree, right? Where it says the highlighted arc between points D and E here, between D and E, measures 45 degrees because the central angle DAE measures 45 degrees. So let me zoom in. So this angle is 45 degrees. And because it's a central angle, then this arc that it opens up to is also 45 degrees. So lesson 2, we start talking about inscribed angles. Now in lesson 1, we talked about chords, we talked about central angles, and we talked about arcs. But now we're going to start talking about inscribed angles. And inscribed angles are angles formed by two chords that share an endpoint, right? Angles formed by two chords that share an endpoint. For instance, this angle here is an inscribed angle. And notice the vertex of that angle is on the circle, and the points where the arc is created are also on the circle. So it is two line segments that share an endpoint. The angle ACB is an inscribed angle. So this angle here is an inscribed angle. Well, in the previous lesson, we talked about this being an central angle, right? So therefore, AOB or BOA would be a central angle, okay? So there's some relationship between these angles and their arc measures that you need to know. All right, if you notice the angle measure here, let me zoom in just a little bit. This angle measure here appears to be smaller than this angle measure here, but they open up to the same arc length, right? So if they open up to the same arc, you would think, oh man, they must be close to being the same. Well, think about this. If this central angle vertex is here and this inscribed angle vertex is here, that is twice the distance to the other side, right? So guess what? If it's twice the distance, it's going to be half the angle. So that means that if you have an inscribed angle that opens up to a chord, the measure of the angle is going to be half the measure of the arc. I said chord, I meant arc. An inscribed angle that opens up to an arc is going to be half the measure of its arc. So, following along, it looks as though the inscribed angle is smaller than the central angle that defines the same arc. In fact, the measure of an inscribed angle is always exactly half the measure its of the associated central angle, right? For example, if the central angle of AOB measures 50 degrees, then the inscribed angle of ACB measures 25 degrees. It's exactly half. Even if we move point C along the circle anywhere else, the circumference of the circle, without going past A or B, this means that all inscribed angles define the same arc or congruent. So this is what that means. If even if I took that point of C, let me use a different color, let's say red. Even if I took that point of C and moved it here, let's say I moved it here, and my inscribed angle was from here to there, and then from here to there, right? It opens up to the same arc, so that angle measure would still be the same angle, right? And if this angle here, if this is 50 degrees, then this one would be 25 degrees, right? Because being a central angle is going to be the same as the arc. Of course, this arc would be 50 degrees. And being an inscribed angle is going to be half the measure of the arc. Okay, lesson 3 summary. In this lesson, we took what we learned about chords, central angles, arcs, and then inscribed angles, and we added on to it. In this lesson, we learned about tangent lines. So a line is said to be tangent to a circle if it intersects the circle at exactly one point. Okay? So notice they say it's said to be tangent to a circle. That's a verb. So being tangent is a verb, right? So it's a noun and a verb. So that means it's some sort of action, right? So it has to be tangent to a circle. So if it intersects at exactly one point, and you can see by the illustration that one point is here, that line, as you can see, only passes through one point on that circle. It's like it just rests on there. It's as if it's a ball and we have a plank sitting on top of that ball. It's only going to touch in one spot, right? That is a tangent line. So suppose line L is tangent to a circle centered at A. That's the illustration we're looking at. Draw a radius from the center of the circle to the point of tangency. So the center is here at A, and notice what it's a new vocabulary word. It says the point of tangency. So where that line intersects is called the point of tangency. Or where the line intersects, or where that point intersects line L, right? You call this point B. It looks like a radius AB, right? So the radius of this circle, remember the radius is from the center to the outer edge, would be AB, right? Line segment AB because it goes from point A to point B. Now, when you have a tangent line to the radius, there's a special relationship that's formed there. This tangent line to the radius forms a right angle. So anytime you have a tangent line to the radius of a circle, it's going to form that 90-degree right angle. So this is that special relationship I was talking about. We're going to use this because this is one of those things we're going to use, uh, and it's going back to what we learned in Unit 5, which is dealing with tangent line. I'm sorry, trigonometric ratios, right? Trigonometric functions. So, and if you recall, one of our trigonometric ratios, and I'll go ahead and write that here again. So remember we use the mnemonic SO, CA, TOA, right? Sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, and tangent is equal to opposite over adjacent. So it's no coincidence that this is called a tangent line and you have a tangent trigonometric ratio, right? And we'll get into that here in the future. It will be soon. We've done a couple of examples in class, but I want to go over some more when it comes time for the leap test. So every other point on the tangent line is outside of the circle, so they must all be further away from the center than the point where the tangent line intersects. Meaning, anywhere else on this line, anywhere you find a point on this line, that point, other than the point of tangency, should be further away from the center of that circle than the tangent line that intersects at the point of tangency. Okay? So if you recall, when we're doing trigonometric ratios and functions, we're using right angles. So let's say, for instance, I have a line here and it's creating a right triangle. Okay, let me just erase some of this. It may help. Let me erase this stuff here. So I just want to go over this example real quick. So let's say I have a point here and this line going here to the center, and of course here's a tangent line, so it forms a right triangle, right? So let's say this side length here of that line segment is 3, and let's say the radius is 4. Then we could find the length of this entire line just by using the Pythagorean theorem, right? But of course, you can see instantly, those of you that remember, this is a 3, 4, 5 triangle. But what's important is, since we do this and we have a radius of 4, if we're looking for this value here, just that little section, let me put it in red. If we need just this length here, we can use what we know to find that, right? And if this is a radius of 4, and we have this line here that also goes to the edge, and this is 4, then this would be 4 and 1, right? So now we have two sections of that same line, and we could find that measurement. Now, this may not seem important right now, it may seem a little arbitrary, but this is something that we could do and you can use here in the future, right? So there will be examples that come up, and you're going to have to remember those things that you learned previously to dealing with circles. So, lesson 4. So now we're starting to deal with um, other polygons, quadrilaterals, triangles, trigons, uh, you know, hexagons, heptagons. We're going to deal with all the different types of polygons. When they're illustrated inside a circle, right, there's a special name that we use for that, and that's called circumscribed. So a circle is said to be circumscribed about a polygon if, let me underline that, if all the vertices of the polygon lie on the circle. For instance, this one, all those vertices are on the actual circle. So therefore, it's considered to be circumscribed. The example next to it, you don't. You have one, two, three of the vertices that are on the circle, but this fourth one is not. So that's not considered to be circumscribed. If it is possible to draw a circumscribed circle for a quadrilateral, the figure is considered to be a cyclic quadrilateral. Cyclic, cycle, circle, right? Not all quadrilaterals have this property. So if you can circumscribe a circle on a quadrilateral, it's considered to be cyclic. Okay? Not all of them can be done. We can prove that opposite angles of cyclic quadrilateral, a cyclic quadrilateral, right, are supplementary. So if it is a cyclic quadrilateral where you can circumscribe a circle over it, then opposite angles are supplementary. Okay? Opposite angles are supplementary. So this is important because we're going to use this to prove certain things or to find angle measures, right? Consider the opposite angles of BCD and BAD labeled alpha and beta, right? So this is alpha, this is beta. Because this quadrilateral is circumscribed in that circle, then I know that alpha and or plus beta is going to equal 180 degrees. They are going to be supplementary. And if you recall, that's what supplementary means. So just to recap, supplementary has a sum of 180. Complementary has a sum of 90 degrees. Okay, so just in case maybe you were confused about that from early in the year when we talked about it, that's just going to reinforce what you should know. All right, so angle BAD is inscribed in the arc from B to D through C, right? So what they're saying is the arc from B to D through C, right? Now, angle BCD is inscribed in the arc from B to D through A. Let me use a different color for that. B to D through A, okay? Together, the two arcs trace out the entire circumference of the circle, so their measures add up to 360 degrees. By the inscribed angle theorem, the sum of alpha and bravo, I'm sorry, alpha and beta, bravo, like I'm still in the military, must be half of 360 degrees or 180 degrees. So angles BAD and BCD are supplementary. So think about what that's saying. That's saying that because these two angles that are inscribed angles, when you add up their arcs add up to 360 degrees. And if you recall, inscribed angles are exactly half the measure of their arc. Then, since they add up to 360 degrees in arc measure, then the angle measures must add up to 180 degrees because 180 is exactly 360 is exactly half of 360 degrees. So that's the big takeaway from this lesson 4 was circumscribed quadrilaterals. Opposite angles are going to be supplementary. Okay? Lesson 5. We saw that some quadrilaterals have circumscribed circles. Is the same true for triangles? Hmm. In fact, all triangles have circumscribed circles. The key fact is that all points on the perpendicular bisector of a segment are equidistant from the endpoints of the segment. All right, so suppose we have a triangle ABC and we construct the perpendicular bisectors of 3 sides. These perpendicular bisectors will all meet at a single point called the circumcenter of the triangle. Notice it's labeled point D in the illustration. This point on the perpendicular bisector of AB, so it's equidistant from A to B, meaning the line segment AB is cut in half, right? It's also on the perpendicular bisector of BC, so it's equidistant from B and C. So it is actually the same distance from A, B, and C. We can draw a circle centered at D with the radius of AD, and the circle will pass through B and C also because the distances between B and D and CD are the same as the radius of the circle, right? So all that means if you take this triangle and you do the perpendicular bisector of each side, which you can see that's what they did. It's perpendicular, meaning it forms a right angle, and it's a bisector, meaning it splits it into two equal parts, right? So they did that to every side of the triangle. And if you recall, that's what we did in class. And that was one of the hardest tasks because it gets kind of messy when you take a triangle and you start finding those perpendicular bisectors, right? We'll go over that here in a minute. When you find those perpendicular bisectors and you draw it out completely, where they all intersect, is going to be that point called the circumcenter, right? And that's where your circle will be centered, and then your radius will just be from that point to any one of those vertices, any one. In this case, the circumcenter happened to fall inside of the triangle ABC, but that does not need to happen. The images show cases where the circumcenter is inside a triangle, outside a triangle, and on one of the sides of a triangle. So this is going to be important too. And the the book didn't really go over this, but it kind of expects you to know it, understand it. So let me just go back to what it just said. All right, so just looking at this. Notice where the center is on each one of these triangles that are circumscribed here. Center, center, center. The first one, the center is on the inside of the circle. The center is on the inside of the circle. So that tells me that this is going to be an acute triangle, meaning none of the measure of the angles within the triangle are greater than 90 degrees, right? So they're all less than 90 degrees. Because this center on the next circle is outside of that triangle, then this tells me this is going to be an obtuse triangle, meaning one of the angle measures in that triangle is going to be greater than 90 degrees. Greater than 90 degrees. And if you think about it, it's going to be this angle here, of course, because notice the arc that's created by that angle. This arc is way more than 180 degrees, right? So therefore, that angle would be greater than 90 degrees. And then the last one, where the center is on one of the lines of the triangle, that circumcenter is on the triangle, then that tells me this is a right triangle. I don't know why this is a right triangle. So if the center is on the triangle, it's a right triangle, right? And it's going to be the hypotenuse. If it's inside the triangle, it's an acute triangle. If it's outside the triangle, it's the obtuse triangle. But let's look specifically at this right triangle. Notice the line, the hypotenuse of that triangle, that's a diameter. It's going from edge to edge and it passes through the center. Now, another thing I want you to notice, since it's a diameter, of course, that means this arc is going to be 180 degrees. So that makes sense because this angle here is half the measure of that arc. So if that arc is 180 degrees, then this angle is going to be 90 degrees. Okay, so that's where we kind of go into lesson 7, but this time it's a little bit more. So you just learned about a circumscribed. Now we're going to learn about a inscribed circle, right? So we have seen that the incenter of a triangle is the same distance from all three sides of the triangle. So here's a new word, the incenter, right? So let me just remind you previously, and this may make sense, we learned the circumcenter, and that was with circumscribed. Now we're learning the incenter, and this is with inscribed, right? So I know I wrote these on the board in class. Some of you may not have noticed it, but the root, circum, circum, right? The root, in, they go together. So you have a circumscribed circle with a circumcenter. You have an inscribed circle with an incenter. Okay, I just want to point that out, make sure everyone understands. So if we draw congruent segments representing the distance from the incenter of the triangle sides, we can think of them as radii of a circle centered at the incenter of the circle. This circle is the triangle inscribed circle. Now, here's the other thing I want to point out. Previously, we took the triangle to find a circumscribed circle for a triangle. We found the perpendicular bisectors. To find the incenter to inscribe a circle, we are looking for the angle bisectors, not perpendicular bisectors, angle bisectors, where we bisect each angle into two congruent angle measures, right? So that's going to be a little different. Just want to make sure that's very clear. In this diagram, segments BD, CD, and AD are angle bisectors. Point D is the triangle's incenter, and the circle is inscribed in the triangle. The inscribed circle is the largest possible circle that can be drawn inside a triangle. Also, the three radii right? So this is the three radii that represent the distance from the incenter to the sides of the triangle, or by definition, perpendicular to the sides of the triangle, right? So they are perpendicular to the sides, but that's not how we find them. We find them by using the angle bisectors. This means that the circle is tangent to all three sides of the triangle. So that last statement is pretty important too. These sides of the triangle are all tangent lines to that circle. So essentially what you're looking at is you have a triangle formed by three tangent lines to that circle. All right, I know that's a lot of information to cover in one video, okay? This is just the notes, just going over everything. In the next video, I'm going to be doing the practice work from these lessons, so it may take a little bit longer, but I just wanted to go over all this so you had time to take time and write these notes if you didn't in class, um, because obviously you don't have your workbooks with you, those stay at school. So this may be a good opportunity for you to catch up or keep up or just to get a review of what we're doing in class. All right, so that's lessons 1, 2, 3, 4, 5, and 7. And the next video, I'm going to do 8 and 10, and I'll do the practice work from that unit. As always, I love you guys. I hope you have a happy and safe Thanksgiving. Hope to see you back soon when we return to school, ready to do your best on this leap test, pass geometry, so you no longer have to see Mr. Ford every day. Love you guys. And oh yeah, don't forget, stay golden, my nuggets.